Welcome to The Explainer. Today, we're tackling something that is literally one of the most critical missions in the tech industry right now. We're talking about taking an experimental machine learning model and transforming it into a reliable, production-grade application. We'll be unpacking the core concepts from Gokul Mohandas' incredibly popular Made with ML repository. So if you've ever built a model and thought, okay, but how do I actually get this out into the real world? Well, you're in exactly the right place.
Okay, let's dive into this because, man, we have all been hit by this universal developer frustration. You know the drill. You spend hours, maybe even days, tweaking parameters. Your model is finally predicting perfectly. You've essentially earned that legendary "it works on my machine" certification. But, yeah, there's a catch. It only works right there on your specific laptop. You're basically stuck in what developers call notebook purgatory. You've got a model that works, sure, but no reliable way to deploy it, share it, or scale it up to actually deliver real-world value.
And look, getting out of that purgatory isn't just a task for some highly specialized data scientist anymore. Machine learning is absolutely a team sport now. Whether you're a software engineer, working in infra, or crunching data, ML is becoming a core part of the products we build every single day. For college grads, mastering this whole process is the key to bridging that massive gap between university theory and actual industry expectations. And for product and leadership teams, having a solid technical foundation in how ML actually gets deployed is just essential if you want to build amazing, reliable products. So this explainer really is for all of you.
All right, let's move into Section 1, Beyond the Jupyter Notebook.
Now, don't get me wrong, Jupyter Notebooks are fantastic. We all use them, right? They're the perfect environment for exploring data, designing, and doing that initial development. It's kind of like a rough sketch pad. But, and this is a big but, responsibly delivering real value requires a major shift in mindset. You simply cannot run a sketch in production. To build a robust system, we have to leave that interactive exploration behind and start adopting strict software engineering best practices.
Which brings us to our next crucial step, Section 2, Engineering Reliable ML Systems.
So here's the absolutely crucial point. We have got to refactor that messy sequential notebook code into clean, modular Python scripts. We really have to start treating machine learning just like any other well-engineered software system. And that means breaking our workload down into distinct, manageable pieces. We're talking about creating separate, well-documented scripts for everything. Training the model, tuning the hyperparameters, evaluating the performance, running inference, serving the application, and obviously testing. This kind of modularity is literally the bedrock of reliability.
Now, as we split our code up into these distinct scripts to train and tune, we quickly start generating a ton of data. And instead of relying on chaotic local directories to somehow remember which model version performed the best, we bring in tools like MLflow. MLflow is awesome because it lets us systematically track our experiments, store our models, and visually compare runs on a really clean dashboard. And hey, if you're working locally, you can easily pull it up right in your browser at localhost 8080. It's a total game changer for bringing order to all that experimentation chaos.
Taking those clean scripts and giving them some serious horsepower leads us into Section 3, Scaling Your ML Workloads. Now, what's really interesting about this slide is how we actually make that leap without reinventing the wheel.
Let's compare where our code is actually running. First, you've got your local laptop. Maybe you're running Python 3.10, and that single machine is acting as both the head and the worker node. It gets the job done, sure, but it is much, much slower. Now compare that to a cluster environment. We're talking platforms like Anyscale or cloud providers like AWS and GCP. By using an open source framework called Ray, which specializes in scaling Python applications, we can seamlessly transition our workloads from that single slow laptop to a massive distributed computing cluster. And the best part, you don't even have to learn a completely new programming language to do it.
To actually manage all this distributed power, we use Anyscale jobs. It's surprisingly simple. We just define our cluster environment and compute configurations in a basic YAML file, specifying things like the operating system and dependencies. From there, an Anyscale job automatically pulls our modular code directly from a remote source, like a GitHub repo that's hooked up to an S3 bucket, and it executes our training and evaluation simultaneously across these incredibly powerful distributed worker nodes. It gives you maximum efficiency with minimal infrastructure headaches.
All right, let's ramp things up for the climax of this explainer. Section 4, Automating Production with CI/CD.
Guys, this is where the absolute magic happens. We're going to take all that tedious manual labor right out of production deployments using continuous integration and continuous deployment. Think of it like a fully automated assembly line. Step 1, you simply push your new code to a separate branch. Step 2, boom, that safely triggers GitHub Actions. Step 3, GitHub Actions automatically runs your anti-scale jobs up in the cloud to train and evaluate that new model. Step 4, it literally posts the actual training results as a comment directly on your pull request. And if you love the results, you just hit Step 5, merge the PR, and the system automatically rolls out your brand new, upgraded service to production. No sweat.
And here is your quick win. The very moment that pull request is merged, Ray is already running in the background handling all the infrastructure. Your model isn't trapped on your laptop anymore, it is instantly accessible. You can trigger it via a quick curl command right in your terminal, ping it through Python, or hit standard APIs. Just like that, your model is finally out there in the wild, completely ready to consume real-world data and fire back real-world answers.
But you know, in the fast-paced world of machine learning, deployment is actually just the beginning of the journey. Which brings us to our final phase, Section 5, the continual learning cycle.
The real world is constantly changing, right? Which means the data feeding into your model is constantly changing too. But because we just built this incredible CI/CD foundation, it makes it incredibly easy to plug in continual learning features. You can set up scheduled cron runs to retrain your model periodically. You can wire up fresh data pipelines. You can set up monitoring to catch data drift before it becomes a problem, and even perform online evaluations. You see, you're no longer just deploying some static frozen-in-time model. You've built a living, breathing system that continually improves and adapts to keep its accuracy razor-sharp over time. We have really covered the entire journey today, from the messy reality of notebook purgatory through modular software engineering, all the way up to distributed scaling, and finally, full CI/CD automation. So I'm going to leave you with this one question to think about. Is your machine learning actually ready for the real world? It is time to take these made with ML principles, apply them to your own projects, and truly deliver reliable production-grade applications. Thanks so much for joining me on this explainer, and I'll catch you next time.